Okay. So I start by thanking Love for asking me to give this presentation, and this presentation is supposed to be targeting this new batch, MS23. And was curious because they were already suffering by my hand in one of the course. So let us see if they can bear with me in this process. Okay, so the talk is about, as you can see, the universe, its advent, and what should we learn from looking around what is us. The as I told in the beginning, the target audience is just the freshers mostly. So the language in which we will speak in this course would be mostly physical rather than mathematical. So there is, for each of the statement we will see there is a detailed mathematical rigor behind that, which we will try to bypass as much as possible without destroying the flow or the accuracy of the statement. Okay? So if you are interested about getting to know the full detail of the accuracy, how much mathematically accurate statement that is, you need to learn certain things about the statements which we will make in this. So I am making it a physical audience oriented discussion rather than a mathematical one, or not for well-trained physicists in this, but just for people who are interested and they want to know what is going on without going into the exact nitty-gritty of things going around. Is that fine? So people, whoever is interested in knowing more should talk to me later or any time in between. But whenever things are not clear, you should stop me and ask me what is going on. Alright? Fine. So let us start. So the advent of the universe is the theme which we will talk today, and we will try to see from the observations of various sources, mostly about galaxies and the collections of galaxies. Is there anything to be learned about how the universe was born? And if there is a preferred model of the birth of the universe, is there enough data to test the possibility of the story which we are trying to weave together, looking at the pieces we have at hand? Okay, so let me start with something very basic and make it more interactive kind of session. So let us see if this moves. Hopefully not. So you see, universe sometimes behaves as static and frozen. But let us put some heat into it. What is this? So I have not named it, but most of the people are trained to identify this as sun, so I will go along with the story. So this is sun. And the sun is roughly, as you know, it goes on with some nuclear fusion going inside it and it emits energy, and we receive energy on Earth, getting warmth and whatnot. The basic estimate, if we calculate for the sun, we will learn that the temperature at the surface of the sun is roughly some few thousand kelvins. Okay? Roughly 5,000 Kelvin. Let us take a ballpark number. If I want to know a distribution of particles having this much of temperature, what would be their average velocities? By atoms, I am roughly taking few collections of protons, is an atom for me. So any, let us say calcium for example, would be some 20 neutrons and 20 protons, and some electrons which contribute nothing to the mass would be the collection called calcium, let us say. Alright? So for that, if I calculate what would be the speed given that they have this temperature, you all know the relation half mv square is kBt kind of thing. So from there you can find out what is the kinetic energy for m object of mass m. From there you can find out what is the velocity they are moving at. For protons and things around protons mass, you will find out the speed is 10 to the power 5 meter per second, which is roughly 100 kilometer per second. This is a very fast velocity, right? Why don't those protons or atoms escape out of the sun?
Gravity.
The gravity of the sun is too big. Actually, if you calculate the escape velocity of this, you will find that it is somewhere close to 10 to the power 7 meter per second, or 10 to the power 6 meter per second up to some fraction. That much be required to escape out of it. Anything below will be bound by the gravity. So far so good. We understand why this much fast velocity is not fast enough to go out. The same story goes for the moon, which is moving with roughly 1 kilometer per second around us. But again, it does not get out of our clutches because Earth's gravity is stopping it. You keep going on, the planets, if you look around the sun, they are also moving with certain velocity, roughly tens of kilometers per second. Some planet is moving at 13 kilometers per second, some planet is moving at 25 kilometers per second, but roughly this ballpark number, they are moving around the sun. And again, as we have learned in the case, that they are also bound by the gravitational pull of the sun, such that this velocity is not sufficient for them to move out. So they form something called a bound system. They are gravitationally bound together, just like atoms on the surface of sun, moon around the earth, around the sun, the planets provide for us something called a gravitationally bound system. The story continues. If I look for the sun and try to find out how fast the sun is moving, or any general star if I look for, typically most of the stars are moving around the center of a galaxy they live in, with velocities roughly 200 to 300 kilometers per second, depending upon where they are in the galaxy. Again, for this much fast velocity as well, it is not sufficient for them to break out of the clutches of the gravity of the galaxy. So you see, starting all the way from the atoms on the surface of the sun, up to the stars moving around the galaxy, the story continues. That the gravity is so strong to capture the velocity, however large this is. The question we ask, is this the story of ever non-ending phenomena, meaning whether we keep on increasing the scale, talk about the galaxies and try to see whether they are moving around something or not? We should try to test that. So actually, if we look for galaxies, you know we live in a galaxy called Milky Way. So most of the galaxies, you do not find them in isolation. They are found in pockets where many smaller galaxies are there. Not smaller really, but many galaxies are there. And these galaxies distribution together form a gravitational bound system again. That is called a cluster of galaxies. So Milky Way happens to live in a cluster called Virgo. Milky Way is in a supercluster rather. It's in Virgo supercluster. So somewhere here. Okay. Somehow I have gone to the end, but you will get there. Okay. So somewhere over here is Virgo supercluster. Inside that there is a Milky Way. Inside Milky Way there is a sun, and around sun there are so many planets, and we live in that. But that is not the only supercluster we know about. Around us there are many superclusters. So people who are familiar with chemistry, this looks like a collection of atoms around in a format like this. So this is an elementary image of something called a buckyball. People are familiar with buckyball? Yes, sir. Fully. So this is, till some time ago, it was the largest known molecule of any atom. So this is 60 carbons stitched together, forming a structure. Apparently, this looks like that. The collection of superclusters may be something like a buckyball with all the atoms here representing one supercluster. So inside atom there will be nucleus and whatnot electrons. Similarly, inside the supercluster there will be galaxies and stars and whatnot. Yes. We are coming to that. But right now we see around us, this is what we see. Whether we are moving away or not, that's what we were trying to learn. Okay? So around us, we are not the special galaxy, we are not the special cluster. There are enough number of clusters around us. And the question is, whether the distribution of cluster gravitationally bound object or not. Just like supercluster itself binds many galaxies around it. Is there a supercluster which makes supercluster as an object of gravitationally bound system? This is the hypothesis we are trying to test. So how do we test that? We will calculate how much of gravitational pull the remaining superclusters will put on one of the supercluster, and what is the velocity it is moving. If the velocity happens to be greater than the escape velocity, it will move apart. If it is smaller than the escape velocity, it will be captured and will form a bound system, just like the story we have learned. So to learn whether the supercluster form a bigger superstructure or they fly apart, we need to learn how much velocity they are moving at this. Okay? So this is the genesis of all the hundreds there are years of search we have landed into to learn about what the different superclusters are doing. Okay? So how do I know that how fast the supercluster is moving? What is the way to find out how fast the supercluster moves? And what distance they are? So to know that, the astronomers way early back in 1930s itself, or 20s, right, they employed a very unique scheme of identifying certain special stars in galaxy. Most of the galaxies do have some special stars, which are called the Cepheid variable stars. These Cepheid variable stars are most of the time most brightest objects in the galaxy before supernova erupts. So they are very bright stars, so you can identify looking at a galaxy that there is a Cepheid star in there. Typically, not always, typically they will be the most luminous object in the galaxy. Now, there are two features of these Cepheid variables which are very useful for us. First, the Cepheid variable, for example, in the image you can see that there is a Cepheid variable inside a galaxy. It also shows variation in its luminosity. Its luminosity does not remain the same every day. So, for example, this is a plot. For example, for some Cepheid variable, its bright as peaked, then dipped, peaked, and dipped, peaked, and dipped within the 2-month separation. So, it has a period of 2 months. Okay? This is what a Cepheid variable could do. But more interestingly, this is not a random occurrence. Now we know about how Cepheid stars work, and from that analysis we learned that the Cepheids have a very peculiar tendency that its period is directly related to its luminosity. Meaning, a Cepheid variable is repeating its pattern very slowly. That means it would be more magnitude in emitting. Its emission will be more magnanimous. It is large emission. So you see the plot, this is the luminosity, this is the variability period. Larger luminosity will lead to larger period time. Okay? So that is how if I see any galaxy in which there is some modulation of the emission in the galaxy, I would learn about how much its luminosity is looking at the period. And once I look at the period, I know the luminosity and then I measure how much I am getting. So intrinsic luminosity, what it is known by looking at its period. How much I am getting can be measured on Earth. Then I can know how much is the distance between me and that object. Because the luminosity intensity received will fall as 1 by r square. Yes, so looking at what I receive and knowing about how it was, I can find out how much distance away the particular galaxy is. Is this clear to everyone? Yes.
All of this is based on this relation that we found, or this correlation that we found over here.
So this is based on the understanding that Cepheid's luminosity varies with its period. This is not a miracle that we observed. Previously it used to be a miracle, but now we have a fair understanding why this should happen.
So first we discovered this as a miracle, and
Then there are explanations for that. And we now think that we know why this happens. And if the physics is same for all the galaxies, it should happen in that galaxy, that galaxy, that galaxy. Okay, someone else has a question. Okay, so this must be fine. Looking at a Cepheid, measuring its period, one would be able to know how far the galaxy is from me. Is this fine with everyone? Yes.
How do we measure the period?
We will just look at the galaxy every day and see if its emission keeps changing in days or not. So it will come back to the same emission after some time. Okay, just like this particular Cepheid, which we were looking at, this had this luminosity on August or somewhere in the mid-August, and then again somewhere in the early October. So roughly 45 days periodicity it had. This is fine. So we know how to know the distance. Secondly, at that distance, what is that galaxy doing? So to know what that galaxy is doing, meaning whether it is gravitationally bound or how fast this is moving, I need to know how fast it is moving, what is its velocity. How do I measure velocity of a galaxy? So Doppler effect. I will look at a particular star and I know how stars are created and they are emitting light of which spectrum. I understand the spectrum of a sun-like star, let us say. So here I have given a comparison of a particular star which is somewhat sun-like, its emission thing, and compared it with the sun exactly. So the red one is the star which I am interested about, the black one is the sun's emission profile. You see they follow roughly the same thing, but with the shifted peaks of absorption. Okay? This shift in peak comes from the Doppler shift. Doppler shift tells you if the source is moving with some velocity and it's emitting some wavelength, the perceived wavelength by the observer who is receding away from the source will be something else. They will not be at the same thing. This is familiar to everyone? So if that is the case, I can look at the spectrum, find out how much is the shift compared to my star, and then I will know compared to my star how fast that is moving. So looking at CFIT and looking at the spectrum, I will get to know two things. How far is the galaxy and how fast that is moving. Agreed? Okay. So suppose I do this thing to humans, that I tell each of you to move to some distance you like and move with whatever velocity you want to move. And then after a while I want to plot that with a distance, what happens to people. Meaning suppose I am trying to plot things. This is the distance. I will tell all of you to move to some distance. Then I will find out who is at distance 30 meters away from me. And what is its velocity. I may find that that person has chosen to run with a velocity 10 kilometers per hour. Let us say. So I will get a number 10 for distance 30 meters. Similarly, I repeat the process for 1 kilometer. There will be some other person. In general, if they are independent person, they have not talked to each other. That person may decide to run at any other velocity as well. So I may find there is a likelihood that I will find some 8 kilometers per second here. Similarly, if I keep doing this, what kind of plot would be generated? It would be a random distribution. Some might be moving in the positive x direction, some would be moving in negative x direction, but it will be filled by a random thing. So if things are independent, they are not talk to each other and they are just doing whatever they want. In general, if I keep plotting, I will get all sorts of velocities at different locations. This would have been at the expectation. So, if this is the case and I do the business for galaxies and galaxies are moving randomly, I should get a scatter plot like this. But instead, in 1929, Hubble did this and he found this. Not a scatter plot, but a highly correlated plot. That galaxies which are at distance some unit are moving with velocity v1, then the galaxy which is twice the distance is moving with twice the velocity in the same direction. So it is not going to the negative side. They are moving in the same velocity, not same velocity, double the velocity, double the distance, but in the same direction. So a galaxy which is 3 units apart is moving twice as far, but in the same direction. So everything is moving away from us, and farther they are, faster they move. This is very unlike this. This tells you this is not by chance. If I look at one true galaxy, it might happen by chance that the distance is double and the velocity is double. But if it is happening with every galaxy we see around us, galaxy clusters rather, then this is very unlikely to be a chance effect. What could be the explanation? Suppose I am sleeping and I wake up and I see everyone is rotating around me. What should I make up? There is a moving platform on which people are lying and it is going around me. It is very similar to this. That I see all the things are moving away from us unless there is some special reason for all the galaxies to hit us. This is not happening by chance. There is some underlying phenomena. And most simple explanation that can happen, the galaxies do not move out of their choices. They are just fixed on a fabric and the fabric is stretching. Just like platform was rotating, this tells you that this is indicative of a possibility which looks like the most possible or plausible explanation, that the galaxies do not want to go away from us because of any special reason. But the fabric on which all of us live, this is getting stretched in all directions uniformly. So in that case only, unless special design of galaxies is taken care, in that case only, all galaxies will appear to move away from us first of all, and that will also happen that the double the distance, double the velocity would be. As we can see from this expression, suppose this is the case on a fabric, there is some particle residing at location 1 and some other particle at location 2. Their distance I am going to call d is equal to some r times our changing function a. R, let us say, is a coordinate location. Call it coordinate 1, call it coordinate 2. Coordinate 1, coordinate 2, the distance between them is actually known by the R, the hypotenuse of this triangle, times a function which changes in time. So R, the hypotenuse, which does not change, but A of t changes. So overall, the physical distance is not just this, but a function multiplying this. Okay, yes. Sorry?
If the speed itself is actually farther, then at some point it also speed of light.
Very good question. Let us see if that will happen. First, let us understand how this is happening. I will come to that question. So this, if the fabric stretches in all directions, if this was 1 unit, this becomes double the unit. Then you see all other, for example, if this was also 1 unit, this has become 2 units as well. And all the directions, in all directions, the point will become double the size. And in this case, this is not happening only around us. This will be a story as seen from the point of view of the second dot as well. The first dot finds that all the dots around it have become farther away from it, and the second dot also feels the same. So all points, it is not the fact that all galaxies are just moving away from us only. All galaxies are moving away from each other. That is like an expansion of a cube. Think of a cube where each edge point is a galaxy and the cube is expanding. It's an infinite cube. Then all the points will find this story. Yes?
Sir, why we are explaining this in terms of some hypothetical fabric? Why we do not say that they are moving apart?
Because I have to give the reason that they are moving apart is a fact. But I am trying to understand why they are moving this particular way, that no one has decided to move towards me, and I move the distance by 2 units, the velocity gets doubled. Can this happen by chance that 10 people moving at 10 different locations or 1,000 people moving at 1,000 different locations have this correlation? If they are all independent, we need to get a scattered plot somewhere. But we do not see that. We see that a clear correlation exists between the distance and the velocity. How can this come about? How does the galaxy number 2 know that it has to move twice the velocity compared to the galaxy number 1? And how does the 1,000 galaxies know that it has to move 1,000 times more velocity than compared to galaxy number 1? And they all have to fit a story, to fit the line. If they have talked to each other a priori that this will what I will do when Hubble looks up, then it can happen. Otherwise, this is one of the most natural explanation one could have. Yes.
So are they also accelerating or?
Till now, let us go slowly whether this is happening or not. So first thing we have learned that the physical distance is changing as a function of time, not because their actual locations in the coordinate system changes, but because the fabric stretches. And this is the A of t captures the stretch of the fabric. So if I want to know how far the physical distance change, I will take the derivative of this object with respect to time. This will give me the velocity at which the galaxies will be moving away from me. R does not change in time, only A changes in time. So therefore velocity will be A dot upon A dot times R. When I take the velocity versus the distance V upon D, R will cancel out, I will get A dot upon A. This will be h. So you see, this will be a linear relation now. V is equal to h times d, like what we saw. So this looks like a possible explanation, apart from one crazy explanation where things have decided to move in this unison such that this effect comes about. Yes?
Sir, why this universe is always expanding? Like,
Why this is expanding? I'm not saying it is always expanding. I'm saying that right now we see like that. First we will see this, that first we have to believe that it is expanding at the moment. Then we will try to build a story if it is expanding right now, what was happening before and what will happen in future. So we will come to that. Okay, so the relation what we saw in the galaxy's distance versus velocity can be plausible. I am not saying that it is the only explanation. As I discussed, the crazy unison is also an explanation. But this looks like one of the most natural explanation one can come up with, apart from having specialized conditions to all the galaxies. So this linear variation what we saw can emanate from here. And with what velocity they are moving? Today we see this much of velocity. That means a galaxy which is 70 megaparsec away. Parsec, everyone understand? This is the 3.26 light year distance. 1 parsec, 1 megaparsec will be 10 to the power 6 times of that distance. So a galaxy is that many kilometers or light years away, that appears to be moving away from us 70 with a velocity 70 kilometers per second. A velocity double that distance appears to be moving 140 kilometers per second of velocity away from us. Is it fine? This is the story for today. Now, as someone asked, if I see this in the sky, that velocity 1929 and today compared to universe, thing is just a blink of a second. So around this time, if it is moving with this velocity, it is very crazy that the universe has decided to start moving away from each other just about the time we started looking them up. This would again be an unnatural thing to assume, that the universe started to move away from each other just now because we are looking. Natural explanation is that they are always moving away from each other and we just discovered it. Right? It would be very, very creepy to think that the universe decided to move apart from each other when we decided to look at them. Right? So if this is the case, then if we believe in this thing that universe was expanding, we just discovered it and we did not cause it, then what does it tell about the past? So it tells about the past. First we need to know why it is moving away. What causes the thing to move away? What controls the growth of A in time? If A changes in time, A dot might change in time, and the Hubble, which gives you the velocity Hubble parameter, can also change in time. So what actually controls the growth of velocity h? So effectively, since we are talking in terms of gravity and whatnot, there should be a framework of gravity which captures this. So I am assuming everyone is familiar with Newton's gravity, right? So Newton's gravity will tell me that mass creates gravity. If there is a massive object, it will create gravity for me. And that's how things will get bound to and whatnot. The escape velocity we calculated was largely based on Newton's theory of gravitation. But if people are familiar, Einstein came around with his theory of relativity, which we will skip over again for today's discussion, but only essential points we will take it. First, Einstein said that Newton's law and other things, they talk about motions in inertial coordinates and whatnot. Let us do away with that. Any frame, not only inertial frame, any frame can be used for computation. So the law should be frame independent in some way. That was the first lesson Newton told. Second thing, he also told that energy behaves as mass, E is equal to mc square. Again, everyone is familiar with that. Thirdly, we know the fact that if a particle's collection is put in a box with some temperature, its velocity imparts pressure on the walls, right? Particles are moving with some velocity, they are impinging on surface and then trying to expand. That is what pressure is about. So pressure is coming due to its motion. Its motion is kinetic due to the thermality inbuilt. Therefore, it's the energy of the particles which appears in some special case as pressure. If I put the energy to zero, pressure will also vanish. Agreed? So energy and pressure are correlated. Pressure energy behaves as mass, and mass causes gravity. So therefore, if I try to club all these things together, not only mass, Einstein's theory should suggest not only mass, but energy and pressure, they should also play in the theory of a gravity, in a correct theory of a gravity. This much is clear to everyone? Yes. Because Einstein told us that you can use any frame and I can convert mass to energy, energy to pressure by changing coordinates. Okay, I go to the rest frame of moving particle, its velocity vanishes. It's only rest mass which is there. So ultimately, changing frame is equivalent to of changing from mass to energy to pressure. So therefore, it should not be one of them which should decide the gravity. It's a collection of that should be. That is the essence of Einstein's theory of relativity in this context. So there is a huge framework of how the galaxies are moving away from us. What we learned that in the previous slide, that the velocity with which the galaxies should move away from each other is this parameter Hubble, which is only function of time. The dependency on r has been killed. Okay, and this is the velocity around us. And you believe into the Copernican principle that our central galaxy is not a special place. It is happening at all other points, just like we discussed. Then we are talking about a homogeneous and isotropic universe. No point is special. Every point feels the same way exactly like the other point. So if I take the Einstein's equation and reduce it for a special case, just like you have certain equations and you want to solve it for a spherically symmetric case, you reduce it to r coordinates only. Similarly, in this case, if you reduce things only to homogeneous and isotropic case, which apparently looks like the structure, then you get something called Friedmann equations, which tell you how the Hubble changes in time and how the A, whose first derivative was giving you velocity, the second derivative will give you the acceleration, is to be known. Remember two things. Gravity was to be caused from energy, mass and pressure, and Einstein's theory will tell you how the rate of change of Hubble is related to energy density, which is rho bar here, and pressure P coming over here. So in a correct theory of gravity, pressure and energy will play, not only mass, and these two will decide how the Hubble will change. For example, now we can look around and find how many galaxies are there, how much energy they are contained with, what is their pressure. I will put that number here and here. This K you can forget. You can put K is equal to 0. K is something called spatial curvature, which observationally we see no evidence of. So K was from a theoretical, more general class, but observationally it looks like K is 0. So forget about this. So pressure, the energy density and pressure are the two elements which together decide for me what should be the velocity and what should be the acceleration. Okay? So this is how I will compute. So I look at the galaxies around and I will find out how much energy density they are containing and how much pressure they have, what is the temperature they are having. I will supply this to the right hand side of this equation and solve the left hand side. Whatever numerical method, computer I can use, whatever way you want to solve, but I will solve this. That will tell me how the Hubble will change in time. H dot, what is H dot? How A dot changes. Once you know H, that tells you how A is changing in time. A dot upon A. Is this clear? Yes. We are first assuming for a universe which is homogeneous and isotropic where the distances change like this. For that universe, what should happen? So Einstein theory tells you if you believe that your universe is of this kind, then the A should change like this. Clear? So I will compute what is the objects around us, what is the density and what is the pressure, and put it to this and find out how fast H is changing and how fast A is changing. Now there is a curious case that if I look around the total matter content, that means energy density and total pressure, and if I compute this, then A will change in time. Today whatever value is there, if it is expanding for all the time, it was so. What does it tell? So if it is clusters are moving away from us to today, and if they have been moving away from each other for all times before as well, that means the clusters which are this distance today were somewhat closer yesterday, and some were more closer a century ago, and some were more closer 1,000 years ago. So this story should continue, and let us find out how much a time it will take till the point all the galaxies come closer and closer singularly to a point. This computation can be done if the equations can be solved. Which equations? These equations. These are differential equation in changing the A, dA upon dt. I will take the square root of the first equation. I will get dA upon dt divided by A is equal to something on the right hand side. And as we have learned in the class as well, once a velocity is given to you, you can find out the trajectory by integrating that. So we will integrate this equation and find out how much of time it will take for the scale factor, the A is called scale factor, the scale factor to become 0, given that it has some value today. Once you do this exercise and put the right hand side to the observed density and whatnot, you will get the answer roughly around 10 to 11 billion years. The scale factor will collapse to 0. That means all the galaxies which are so far away and moving with that velocity will collapse to a point within 10 billion years. This, according to this analysis, should be the time of the universe. This is born from a point and started expanding away. This is colloquially called the Big Bang. Note that Big Bang is not a point somewhere in space. All the points were created simultaneously there. No point can claim that everything has collapsed onto me. All the points are coming closer to each other. So there is no preferred center. Big Bang did not happen here or there. It happened everywhere. Okay? So something popped out of nothingness. That is called the Big Bang. What exactly it is, we do not understand. But this is why we have given this as a fancy name. Alright? So this tells you, yes?
But like now we have calculated this time using today's condition.
Using what we see around today and using the Friedman equations, we try to find out how much time in the scale factor will collapse to 0.
So we are assuming taking today's condition, 10 billion years before we.
No, so we are saying that today what we see, how many galaxies, how many matter is there, and we know if this density, so you see energy density is somewhat which is sitting in the driving equation, and pressure. Given this energy density and this pressure, we know how to calculate what will happen to them if we go in the path. We do not keep it constant. They will also change in a particular way. For example, a particle is put in this box. There is an energy density. Roughly the mass times c square will be its energy. The volume of this class will be its divided. If I divide by that, I will get the energy density today. If the box size becomes half, the energy density will shoot up. Because the volume has changed a half, but the mass has remained the same, E is equal to mc square. So roughly those kind of analysis we put to all the matter we see. Okay? And then we calculate under that change what we understand should happen for the matters we see around that. What should happen? So that answer you will get of roughly around 10 to 11 billion years. Agreed? This is fine with everyone? Any confusion? So this is a very nice looking numbers of roughly tens of billions of years, roughly 11 billion years let us say. But unfortunately this is a wrong answer. And how do we know this is a wrong answer? Because the Milky Way itself is roughly 13.6 billion years old. So the Milky Way is supposed to come out from the Big Bang, and Big Bang happened at roughly 11 billion years ago. Then how it is aged 13.6 billion years. And this is not only true for Milky Way. Most of the galaxies what we see around us are roughly around this ballpark, 13 to 13.8, 13.9, closing into the 14 billion years. So these are these old. So clearly what we have seen and we try to extrapolate in the past is not a good story to look at. Yes?
How do we arrive?
This is for you to find out. How do we know without, because looking at Milky Way is not a cosmological problem. So this is the homework exercise for you if you want. Try to find out how do we know about the age of Earth, Sun or the Milky Way. I will give you a hint. There are some special materials. This is like carbon dating if you want. There are some special material like beryllium, lithium, whose dependency change in time according to a particular way. Looking at the beryllium content in a universe, in a galaxy, you would know how much age it has. Yes? So it is roughly a carbon dating. Okay, so this we learned that the velocity what we see today and we extrapolate it back, the velocity would change in one particular way and we will end up on 11 billion years. But there are things much older than that. So somehow we have to slow the expansion down. If it is slowing in the past, that means it will take more time to become this size today. If it is faster, it will take no time to reach this much of size, whatever we see today. So somehow we have to make it slow down in the past, such that it takes more and more time to become this size today. But this is the problem. We can try to do this, but this is a solution of addressing this. This can happen. I slow down the galaxy by doing something. This will become 11 billion years, will become 15 billion years. But the process by which I can slow it down is a problem.
Is it arbitrary? Like we are noticing that our previous model is wrong. And then we are deciding that it should be greater, but how
What is the mechanism to make it larger?
Yeah.
If you believe that if it is the H is 70 kilometer per second today at 1 megaparsec, if that was the same velocity, you can find out how much time it will take. It will take even less time. It will give you 5 billion years. If you want to make it, it has reached 70 kilometer per second by going from a velocity which was something else. It will take more time to reach. If you assume that it has reached up to today 70 km per second, slowing down from a very large velocity, it will again take a smaller time. So ultimately, I know that somehow I have to slow h down in the path. Okay?
In the past, since things were closer together, the gravitation be strong. Like that.
That is what we are coming at. But first conclusion, how it is happening, why it should happen, this is a secondary. But unescapable conclusion from this, that the given material and given h would not work. We have to do something to the material and h. Only way we can do is to slow things down in the path. Then only we can generate more time. Right? How do we slow things down? And if slow things down, what will happen? So, for slowing things down, first, whether this happened or not, this is a mathematical trickery we are going to do. That we will accommodate something and then it will become slowed down and we are happy that now 13.6 billion year old object can form. But that is just mathematical jugglery we have done. Whether this happened or not, truly, how do we know? So this was a very many decades exercise. And this was actually answered at the end of 20th century, somewhere close to 1998, where people like Rees and there are huge collaboration, which looked at one more trustworthy object called supernova 1A. Supernova 1A is the end stage of certain stars, which collapses under its own gravity. It is so intensely gravitating object that it pushes all the electrons inside the nucleus, converts all the protons into the neutrons, and they emit photon and neutrinos away. So ultimately, some type of stars at the end become neutron stars, and this process of last leg of turning into neutron star emits a huge radiation. And it outshines all the stars in the galaxy. One supernova, one star's death sound is much louder than the entire galaxy and all the stars put together. So that is a very bright object. You see one, you know that there is a star which has died and become neutron star. And at what mass that will happen, that can be calculated. That is a very simple calculation. How much of gravity do you need for electrons to be pushed inside the nucleus? So that is a unique number. That is roughly somewhere close to 2.1 to 2.2 times of the mass of the sun. The sun will not do that. Sun is not massive enough. Some other stars, which are roughly twice the mass of the sun, they are able to do that. Alright? So once we know that which mass objects will do that and how much energy it will be released, we know the luminosity with which they are created. And again, whatever we see is the apparent magnitude, we know what is the real magnitude of emission. Again, we can calculate how much distance away they are from us. And looking at the spectrum once more, I can find out how much velocity they are moving at. So Cepheid stars were bright, but supernova 1A is much brighter. So therefore, we can look more in distance galaxies. Cepheid, we can look around, but supernova 1A gives us handle to go more along the x-axis, move more along the distance. And if the story of the Hubble was correct, that the distance, the velocity keeps on piling up in a linear fashion, what we could have gotten was this dashed line. But what we see is that after a while, till the time we probe very close to this region, it looks like that it is moving linearly. But as supernova 1A were used, this is like the Cepheid zone, where we use Cepheid only. But as supernova 1A started piling up, we saw that there is a clear tendency of moving away from the straight line. That means indeed galaxies much farther away are moving with smaller velocity compared to what Hubble's linear law would have predicted. But the distances the galaxies are farther away from us, it takes more time for the light to reach from there to us. That means the distant galaxies which we are looking at more older things, more things of more past. So that tells you the objects which are farther away are living in past time, and they were moving with a velocity slower to what we would have anticipated. Reverse this story. There are the stars there are the things which are moving slower when they were past in time. Coming close to us, they started picking up pace. Things when we came up towards us, nearby things are near in time as well. So they are having the larger velocity. That means the expansion was happening at some velocity initially, and it started building up velocity later on. Meaning, as we come towards present epoch, the velocity is not remaining constant. It is not decaying down, it is picking up. Is this clear? Is this message clear to everyone? Yes.
So why does this data come from the Cepheids and only from...
Because Cepheid have bright objects, but it is not absolute bright. You cannot go much distance with the Cepheid. Cepheid explodes only this way.
Oh, so okay. So
Supernova 1A gives you... Yes. Okay, it looks like... I think we started somewhat late as well.
Yeah.
So let us see how fast we can move ahead with this. Okay, so this trend that indeed the things were moving slowly in the past and they have picked up pace is not only our mathematical generally thing, it is realized, it is seen that this is what it might have happened. Now the question comes, why this happened? Why velocity picked up? Because if the universe was born with a blast, in blast what happens? Fragments fly out, and after some time they fall at some place. Their velocity becomes smaller and smaller and diminishes down. So this was the case of the universe. It was born with a big bang. Its constituents should have flown apart, which we see, but they should have slowed down. If friction is significant, they should have slowed down very quickly. Even if friction is very weak, they should at most remain constant and very slow decay should happen. But in none of the cases, they should pick up velocity. Because at those large distances, only gravity is the working force we know. There are four forces: electromagnetic, gravity, weak and strong forces. Weak and strong forces only work within atoms and nucleus. Actually nucleus. Much larger distance we do not see any evidence. Galaxies do not carry a net charge. So therefore there is no electromagnetic interaction between them. Only gravity should work, and gravity by and large is a pulling force rather than a pushing force. So whatever gravity should have done, they should have tried to stop going away. But now we see the evidence, the things are happening the other way. That things are picking up speed despite gravity acting on it. What can do that? Why it should be there? So again we go back to the Friedmann equation, the Einstein's equation in the special case, and we ask when this can happen. So we look for the equations again, acceleration equation particularly. You see that acceleration equation, this is acceleration, comes with a minus sign. So as long as this object is positive, g we know is a positive, the whole thing should have an overall negative sign, that is negative acceleration, which is slowing down. But the galaxies closer to us tell us that close to our time, they started picking up pace. That means somehow this combination turned negative closer to today. Can that happen? We do not know anything which can turn energy density into negative thing. Energy is a positive concept in most of the things. Pressure, we know in certain cases can become negative. A collapsing thing. There are certain examples which I am happy to discuss, but those are not very normally occurring things. Under certain exotic conditions, pressure can be made negative. And if pressure becomes sufficiently negative enough such that this outsmarts the energy density, then overall negative will come to full positive. So you need not normal matter, but some special matter which has a tendency to generate negative pressure. And that negative pressure object is called a mysterious object which we do not understand, but we know this property it should hold, and therefore we call it dark energy. So the dark energy is supposed to cause the systems to start picking up pace closer to today. It did not act much in past, but today somehow it has come up and it has started things, caused the things to accelerate. Again, if we try to know what would happen, we should appeal to full Friedman equation. That is to say, there is normal matter which we see around us, acceleration tells there should be exotic matter, which today at least is outsmarting the normal matter, such that the overall energy density and overall pressure put together is a negative number. But if we try to find out, for example, if I give the example of a particle whose mass is there in the box, if the box is made half, since the volume has shrunk, its energy density will rise, right? Similarly, for suppose a photon is put in the box, if the box is shrunk, volume will again become half, but the wavelength will also become half. If wavelength becomes half, energy becomes double, because frequency becomes double. So for massless objects, apart from volume change, energy also changes. So it rises faster. So radiation's energy density rises faster as you shrink the box. Massive objects' energy density rises, but not as fast as the radiation. This exotic matter, which is supposed to put negative pressure, if you compute, you have to do some amount of exotic matter analysis in field theory. If you do that, you will find out its energy density changes marginally under volume change. Most of the time, exotic matter's energy density does not change much, it marginally changes. That means the energy density of this dark energy which is causing the universe to expand and accelerate today, the energy density is roughly the same with which it was born. It has not changed under expansion or dilution. Its energy density was way too small at the early time, such that when the universe was very sized, then the normal matter's energy density peaked up, radiation energy density peaked up, its energy density was about the same value it is today. So therefore it was so suppressed. But as the universe expanded, the normal matter's energy density falls. The exotic matter's energy density does not fall that fast. So ultimately there will come a time when all other energy density, normal matter has gone down to nothing, while the exotic matter energy density is still at the same value, it will fall. And it will cause the things to start accelerating. Is this clear? Is this picture clear? So this again gives a mystery to us, that why the exotic matter was born with energy density just as much to start accelerating today when we started today. It was not accelerating much in past. It has started accelerating somewhat closer to today. In the past, normal matter was driving things, velocities were smaller. Now the velocities are picking up. So somehow, this dark energy is intimately tied up to when the planets were being born and we were coming into existence. At that time, the dark energy decided to show up. This is one of the very mysterious problems known as the coincidence problem. Is it just a coincidence that these things will happen together? By chance it has happened, or there is a bigger picture on that? Nobody knows the answer. Okay, so to answer what causes the universe to expand, an exotic matter, we do not know. We call it dark energy. Yes.
Isn't this just thought for luminescence, ether kind of effect?
Sorry, ether kind of things?
Yeah.
No, it would not. I will tell you it would not. If you want to discuss, we can do it separately. Ether would not do this. Okay. All right.
So this,
Yes.
so we since okay, it's called dark energy because it does not interact with light. Right?
No, I'm not calling it is not interacting with light. I'm saying that we do not see it around, but still it contributes into acceleration. We see only luminous objects, its energy density, matter, and other things we put in. Then ultimately it leads. Dark, the thing you are probably hinting at is something called a dark matter, which is a separate story. Dark matter is not dark energy. Dark energy is something very different. Dark matter is something which decides what happens inside a galaxy. This is which will decide what happens between two clusters of galaxies. Okay. So this is one of the mysteries, that why it has popped up now. Why did it pop up half the time of the universe age or something like that? Actually, it's not a good phrase to say half the time of the universe age, but anyway, it has popped up around the time when galaxies and other things, planets were being formed. Yes.
According to Einstein, energy can be converted into mass, right?
Energy can be, yes. All energy is mass, let us say.
Can dark energy be converted into dark matter or dark matter into dark energy?
All we say that energy can be converted into mass. By mass is not a name, it's an object which causes gravity. So dark energy, whatever you call it, converted into mass, it causes gravity. And that's why things accelerate.
Is it possible?
So don't get fixated on the name dark and energy. There is some mysterious object which contributes into the expansion of the universe in a way that it accelerates. That's all. Okay? Alright. So this is the story which we learned, that there are photons today, there are normal matter today, this massive object, and there are some hiding dark energy today, whose energy density will start building up as we go back in past and past. So photons energy density will increase very rapidly, because apart from volume change, its wavelength also gets shrunk. So they will become more and more energetic. And when the photons become more energetic, they are very intolerant objects. They would not see any atoms around. If they have energy, they will tear it apart. So once the energy of the photons increases, they will not let any atom remain at peace. They will rip it apart. So all the atoms are broken into its constituents. Further, its energy will keep rising on, and all the constituents, if they have enough energy, they will try to break the constituents as well. Molecules will break into the atoms, atoms will break into nucleus and electron. Further, if they have sufficient energy, they will try to break the nucleus as well. So if you go back in past and past, there should not be any molecule or atom or stars or anything. All the things just to the bare minimum. No bound object. Photon's energy will shoot up so large that any bound object will be disintegrated by impinging on it. It will come with so much energy that it will disintegrate everything around it. So very close to the universe. So this is the start today. If you go back in past, they all become ionized, disintegrated. Ultimately, you will have a plasma of bare minimum things, which will keep shrinking lower and lower. And whatever happens to the plasma, which advanced theories will tell us, that should have happened. But this is a story which we believe largely looking at it. This is fine? Okay. So there is a curious thing which will happen if we take the story forward. That means, at the beginning of the universe, the photons and other things would have been born with very high energy, and they will not let any atom or any bound object to form. But as the universe expands, the volume will become large, the wavelength will become large, the energy density will go down. So photons energy will keep getting down as the universe evolves. So energy will come down to some scale when atoms will start forming, when molecules will start forming. When it would lose energy so much that it is unable to ionize the hydrogen atom. Hydrogen atom gets ionized at roughly 13.6 eV, right? The 1s state has this much energy. If you want to take that electron out of the hydrogen atom, you have to supply 13.6 eV. But as the universe progresses, somewhere will come a time where the photon's energy will go below 13.6 eV. At that time, it will not be able to ionize a hydrogen atom. Okay? From that time onwards, it will lose the capability of doing anything mysterious to any bound object. And it will pass without affecting anything else. So that is a special moment in the history of the universe, where the photons stop talking to everything. That is called last scattering surface. Last time, the electron talked to any matter. Okay? After that, it will just free stream, not doing anything to anyone. And the prediction is that if this story is correct, those photons not talking to each other should be coming to Earth now. And we should be able to see those. Those, when they stopped talking to all the present matter, from that point onwards, nothing special has happened to them. Only its energy has diluted, its volume has diluted, so effectively energy density has come down. But it has not done anything mysterious in the way. So they are coming up to us containing the same information they had till the time they stopped interacting with other materials. So the image is captured at the last time of talking, and after that they are just getting stressed and getting down in energy. So if we receive it today, we can try to learn what was the atmosphere when they stopped talking. Right? This is like a last cry they put in after the interaction. So we can look at 300 or 400,000 years after the beginning of the universe. Compare it to the 14 billion year time we understand also, which is like 1 millisecond in a lifetime of a person. What happened at 1 millisecond during the birth of a person, that information is received after 70 years of the person's age. This is as good as that. So this radiation is called cosmic microwave background radiation. It's a cute story that it was discovered accidentally. People were trying to look for something called microwave radiation from other processes, but they were getting noise here and there. So they tried to put the system here, there, everywhere, but they kept getting this noise. So they tried to rule out what is causing this. Ultimately, they ruled out everything which could have given this, and they ended up saying that it looks like there is a background of bombardment of photons of this much energy today or not. We do not know the reason. But around the same time, this was 1965. Around the same time, there were theories which were suggesting this formation of CMBR. So this was a very curious case where the theories and the experiments were hand-on, independent of each other. No one was looking for the other, but they were discovering the same thing, one mathematically, one experimentally, around the same time. Okay? Once they stopped talking to protons, electrons, and so or any matter, after that they will just free stream. Somewhere in the future, the galaxies will form and they will start drift away. The mass of the galaxy will create a gravitational potential for them, because Einstein has told us any energetic object is as good as having its mass, and mass causes gravity. Photons also have some energy, therefore equivalently they have some mass, and Newton's gravity tells us that two massive objects get affected by gravity. So once they stop talking to hydrogen, helium, those kind of things, after that whatever could have happened at best is that the galaxies which will form in the future, they will mend its trajectory by applying gravitational force of it. So straight moving photon will slightly get bent. There is something called light bending by gravity. That would have happened. Okay? So somewhat that would happen, but that is very marginal effect. So the prediction is that once the photon stops interacting with normal matter and goes streams by almost freely, marginal gravitational effects will come in between, and by and large we will receive them as they were at 300,000 years ago. Alright? So, this is people try to look for. Once this Penzias and Wilson's thing was taken seriously, we started sending satellites looking at whether this thing exists or not. So this is as good as being on Earth and looking around our sky, make a cut and stretch it. Just like cut a globe and stretch it, it would look like this, right? Similarly, the sky around us, we map everything, what is the radiation we are receiving, and stretch it, we get this kind of image. This is Kobe, some satellite mission which was sent in 1990s, 1996 around that time. In early 2000s, WMAP was another satellite mission which was sent, and late 2010 onwards, there was a mission called Planck which went and zoomed into this. You can see the evolution of details. Previously, we had not so much of resolution in our satellites, but as the time is we have this kind of structure. We see that we are bombarded from all sides by photons of CMBR origin, which is roughly 2.73 Kelvin. The blue dot and the yellow dot roughly tell you about the change of temperature along different directions. Some yellow dot is slightly higher than 2.7 Kelvin, some blue dot is slightly cooler than the 2.7 Kelvin, but not much. Actually, this is the best black body known to humanity till date. Whatever we are seeing is the example of most perfect black body we have ever seen in any experiment. The cold dot and the hot dot. So base temperature is 2.73 Kelvin. The red dot is hotter by 2.73 Kelvin by a microkelvin. That is to put 4 zeros after 73 and may you at the 7th decimal place you can put something else. And the cooler thing is marginally less from 2.73 Kelvin by roughly a microkelvin. So as uniform this is. So this tells you whatever the theory was predicting was indeed coming to us. And it is very gratifying that whatever it was predicting indeed comes. By looking at why this became hot in this region, why this became cold, we can try to learn what was the condition before and how galaxies would have formed in between. Okay? So this captures the information of the time where there were no galaxies, nothing. But it tells you the potentials of the things which could have happened. For example, if I compare this image with today what we see from not CMBR but optical photon, actual galaxies. You see the actual galaxy map looks extremely similar to what the CMBR radiation map is. So this gives a sudden gush of feeling that wherever I could see this hotter thing, there is a galaxy over there. Wherever there is no galaxy cooler thing, there is an empty space in today's world as well. It looks like these marginal fluctuations what we see of microkelvin origin, they are not big fluctuations. Ultimately, during the evolution, their potential looks like that they grew into something like galaxies of today. So this is like very early seeds of what would have become the galaxy clusters today. Alright? But this is very, so CMBR radiation which we see is remarkably homogeneous. It is roughly the same temperature everywhere around. But this presents a very mysterious condition as well. From this accelerating universe calculation, this 10 or 11 billion years age now gets corrected to roughly 14 billion years. So we know that if the universe has expanded with the dark energy also thrown into the game, the age becomes not 10 billion years but roughly 14 billion years. So we are safe in terms of objects we see around. But recently, some group has claimed that they have seen a galaxy at 14.55 billion years, which is again people are looking at, but their error bars are large. They are not certain that it is really 14.55 or something else. But that game is on. By and large, we believe roughly the age is 14 to 15 billion years, and from the time t is equal to 0, 300,000 years apart, photons stop talking to each other. Stop talking to anything. So they free stream after first 300,000 years, and for the remaining part of 14 billion years, they were just moving around. But this gives you a very drastic conclusion. The homogeneity which we see is remarkable. The temperature receiving from this part of the sky, that side, is by and large up to a microkelvin, same as the temperature coming from that side. So that side and that side decided to come to the same temperature. And they stopped talking to each other some 300,000 years after the beginning of the universe. So I want to calculate how much of the space they could have covered in first 300,000 years. If it is sufficient time for this portion to get into touch with that portion. This is to say, if I can plot things. So suppose this is the condition as t is equal to the last scattering surface, which is 300,000 years roughly. And this is the portion which was universe was born with, t is equal to 0. So each point here, if light rays are received by this, it must have received signal from only a portion of initial data. While this point here will have received light-like information or anything within this patch. So the condition here should be made up from condition here, and condition here would be made condition here at the last scattering surface should be made up from initial condition at t is equal to 0 of the portion here. Is this clear? Because things can at most move faster up to light. Anything from here to reach to this would require faster than light movement.
So that equal to 0 was the size 0 of
Physical size is 0, but I am writing in the coordinate basis. I will multiply A is equal to 0 whole thing so that it will shrink. Right now I am writing in the coordinate basis without A.
So, but if the size was 0, wouldn't the distance have been like to travel from any point to the last action?
So it was not this 0 for all time. At one moment it touched 0, but there is an expansion rate and there is a light moving rate. If, so both
was faster than the left, right?
so things, so that I am not saying yet, but how fast the things are expanding versus how fast the light is moving, they have a competition. And if one is faster than the other, it can happen that only a portion can be connected, meaning this condition here can be decided by condition here only, this patch only. Condition here can be decided by condition at this patch only. But at the end product, I get condition here and condition here are the same. That means condition the universe was born with here and born with there would be remarkably same. That part never talked to this part, but still decided to come up with the same temperature. This is like someone has come with a red t-shirt in this room. You are also wearing a red t-shirt. This is coincidence. But if everyone else is wearing a red t-shirt, I will be curious why this is happening. I will trace back if every one of you talk to each other to come in the talk with a red t-shirt or not. If I do not see any evidence of you ever talking, this is mysterious. This is as crazy as this. The photons which never got to talk to each other decided to come at the same temperature all around us. Why this could have happened? Okay? This is the curiosity. So, this is something called a horizon problem. The horizon of thing what we see is finite, but the spread of uniformity is full sky. There is no, if we believe in the calculation and causality and whatnot, it tells you only things should look homogeneous only in 2-degree patch of sky. But I see all around 4 pi of the sky, there are homogeneous and isotropic. This is called horizon problem. How to get around this? So, just a second. Just 3-4 minutes and I will be done. Okay. So this proposal, this homogeneity haunted theorists for many time. That why this is so homogeneous. Standard evolution story which we believe into cannot predict any way of homogenizing things as the. So this has become thermal. For things to become thermal, there is a the thermal time scale in which they get equilibrated and whatnot. Universe did not have enough time to equilibrate to same temperature, but still it did. How it could have happened? So this was debated by many people for very time. The only possible natural explanation, apart from somehow the universe was grown as crazy as this, was most likely there was another piece of dark energy not appearing later in time but very early in time as well. So there was a brief movement of a dark energy driven expansion. Today we see the accelerating universe. In the past, dark energy was subdued, so it was deaccelerating universe. But if we want the CMB to become as homogeneous as they are, that is, it is natural to put in another dark energy which becomes important at very early time for very small period. How small? For 10 to the power minus 35 seconds it should last. And within that time, dark energy accelerates things and expands things. The universe should grow to become 10 to the power 25 times of what it was born with. So whatever size the dark energy kicks in, within no time, 10 to the power minus 35 seconds, if it expands things up to 10 to the power 25 fold, then the problem of homogeneity is solved. It looks like again a theoretical mystery or mathematical jugglery that this can happen. But is this what happened? This might have happened mathematically, but who is to tell that this really happened or not? To answer this, we can try to ask what else it does apart from homogenizing the CMB sky. Is there any other prediction which it does? Or we are trying to fit data to fiction? So the new prediction which people try to come up with, first thing, if it is accelerating too much in no amount of time, that means it was born with really tiny size. And when it was really tiny size object, laws of macroscopic, large size objects should cease to act on them. The small particles do not follow the usual Newton's law or even Einstein's law. A new theoretical paradigm opens up for them. That is known by the regime of quantum mechanics. I hope this is familiar to everyone, that microscopic particles, tiny objects, They rather follow quantum mechanics rather than the usual Newtonian or classical physics. So the proposal is that why this would not be true for universe completely, because universe at some instant of time when the first dark energy phase was there, that is called the inflationary phase, just to distinguish it against the present day dark energy phase. So early time acceleration is called inflation, late time acceleration is called dark energy. So early time dark energy or inflationary phase to happen, it should have demanded very tiny size. Because if it were not tiny size, it has to grow 10 to the power 25 fold. All the galaxies will be much away from what we see today. So indeed the universe must have been born with really tiny size. Such that even after 10 to the power 25 fold increase, it remained not so big. So during the inflationary era, if it was too small, quantum mechanics should take over. And quantum mechanics, if any of you are familiar with, is a theory of probabilities. It would not tell you what would happen. It will tell you what is the probability of something happening. It tells you all things can happen with certain probabilities. If the probability is 0, then it will not happen. But if the probability is 10 to the power minus 35, once in 10 to the power 35 times it might happen. Okay? So, just like it is a coin toss, it's average, it will tell you about, on the average, what should you expect. From probability theory, you know a fair coin has a 50% chance of head and 50% chance of tail. But it does not tell you that in the 10th toss or 9th toss, what should I get? It will just tell you if you do for 3,000 times, roughly 1,500 times you will get head, and roughly 1,500 times you will get tail. It will not tell you what will exactly happen. It will tell you about averages. Similarly is quantum mechanics. It will not tell you what will exactly happen. It will tell you what to expect. Okay? Another thing quantum theory comes up with is it allows for mysterious phenomena to happen as well. For example, you can ask this question: what is the probability if there is no particle in the universe? After some time there is a particle in the universe. Is this a possibility? Quantum mechanics again comes and tells you, let us compute this probability. From the formalism of quantum mechanics, you can find out this probability. And it will tell you that as long as the system does not change, it does not expand or collapse or move or this thing, that probability is essentially 0. So if there is no particle, it will remain no particle if the things are not expanding. But if things start to expand, collapse, move or something, then there is a non-zero probability of particle popping up. This is like a magician pulling out a rabbit from the hat. Unless the magician waves the wand, the rabbit would not come out. So waving of wand is equivalent to expansion. If expansion happens, particles can pop out from nothing. This is one more prediction. Just it is allowed probability. If you calculate what is the probability of that happening, it will become non-zero with a very small number. Very less likely that will happen. That's why we do not see in usual case when this room is double, we do not see new students. Actually we do see, but they are through admissions, not quantum mechanics. Okay, but this tells you that new and new particles are created, something called quantum vacuum. There is a hidden sea of particles which are not seen to us, which is called quantum vacuum, and there are some magicians doing something, but once in a while they can pop up if the universe is expanding. And inflation tells us that very early in the phase it expanded really fast. So therefore it would have created many particles. And now bring Einstein in. Any particle popping up will have energy, it will have mass, it will gravitate, attract other particles, form a structure. So if you are born with nothing, you just expand, new particles will pop up, they will form atoms, galaxies, whatnot, galaxy cluster, whatever we see. Okay? So, this is what quantum mechanics tells. This is a probability. And as we discussed, quantum mechanics should answer you what should you expect. So, I would not be able to tell you what exactly will happen. Quantum mechanics will tell you what is the probability that a particle will be popped up there and particle will be popped up there and that particle will evolve into a galaxy here and that particle will not evolve into a galaxy there. All these probability can be expected, calculated rather. So, therefore, we can ask the question, given the fact that there is a particle which has popped up here, what is the probability that another particle will pop up there? This probability quantum mechanics can give the answer. I can compute this. Similarly here and there and there, where and there, and ultimately average that out. So ultimately this tells me the likelihood of finding two particles at some distance apart. This computation we can do from quantum mechanics, and it gives me some answer. This answer has a particular structure on the cosmological science scale. Scale is meaning wavelength or the size of cosmology of galaxy intergalaxy distance. The probability should become independent of the scale, k to the power 0, meaning constant. It does not change with size. For large enough size, it becomes a constant probability everywhere. This should have happened according to quantum mechanics. If I look for observation, forget about quantum mechanics, look for galaxies and do the same computation, given a galaxy here, a galaxy there, a galaxy here, no galaxy there, multiply them together and average that out, I get an answer that tells me that it is the probability of having a galaxy here and a galaxy there is k to the power n minus 1, where n is very, very close to 1, 0.98 up to error margin it is 1. So whatever we see the galaxy, the average correlation, this is called correlation, galaxy being here, probability being there, that is exactly matching to what inflationary physics has predicted. Apart from solving the horizon problem, it predicted something for you. That, or if this is the scheme, then you should expect galaxy here, there, with this law, k to the power 0 law. And indeed, when we do the experiment and observation, we get a number very close to 1. So it looks like that prediction of inflation is in town. That means, that's it. Have we learned enough about universe? Are we done? Inflation happened, normal matter took up, then the dark energy comes. Is this the story to go with? This is up to you to decide. Because inflation, as we discussed, created particles for you, which became later on the seeds of galaxy and formed a galaxy. But it did not create only electrons and protons and other things. It created photons and gravitons and all sort of particles in the universe. Okay? It also created electromagnetic field for you. When the universe expanded, there was no electromagnetic field, which is photons, it would have created for you. The same computation which gives me a very good fit with the galaxy correlation falls short of predicting what should be the electromagnetic field in the universe. If I calculate how much of magnetic field the inflation quantum mechanics predicts, I find a theoretical number much shorter than what we see. Is it a problem of inflation or a problem of the electrodynamics as we know it? Maybe the laws of electrodynamics we know at those energy scales change. I do not know. It should have also created gravitons for you. That means gravitational waves should have been generated. Right now we are seeing gravitational waves from nearby objects. We have no evidence till now of gravitational waves, just like CMBR radiation, there should have been a graviton radiation background. We have not seen any evidence of that gravitational wave, of primordial origin. We do not know. Similarly, if a particle can pop up from vacuum, you can ask the question whether a black hole can pop up of a vacuum or not. The quantum mechanics tell you there is a non-zero probability of that as well. That means once in a while, a black hole should have also formed. Where are they? Why don't we see them? Some people believe they might be some part of something called a dark matter. But black holes by their name are not to be seen, only to be filled. Dark matter also does the similar kind of thing. But there is some tussle going on whether the black holes, if they are generated, are the component of dark matter or not. The jury is out, there is no decision on to this. Whether the black holes are the dark matter, they are a part of a dark matter, or they do not exist. Nobody knows. So, how to decide what is the full story? We have seen only one property of correlation, and it will be too premature to declare decisive victory with one computation and one set of observations. Maybe there are mechanisms which match with this one computation, but other observations are different. So one needs more and more computation and more observation. Unfortunately, these observations are not tabletop point, such that you can arrange things on table and on a lab and do. It is witnessing the whole sky with precise expertise or skill in that thing which you are looking at. You saw the images of Kobe, how diluted they are, and then we have to refine over 30 years to get as detailed as the Planck missions data. So it is a large collaborative effect one has to come up to look for more hidden properties to declare whether inflation, it is a good hint. Whatever inflation predicted apart from solving one of our problem of horizon looks like to be the case, but there are shortfalls as well, like enough magnetic field is not generated. Enough type of some galaxies are also not generated. So there are classifications what inflation has not yet achieved. Okay? So we have to be looking at the right region between the empty space, right place with right expertise. Just wait, I will just conclude and then I'll take question. And this is the case. So the take home message, I will just give you a fact sheet that we think that we know for sure. Again, I'm saying it is not that we know for sure. We think that we know for sure. First thing is that all the galaxies which we look apart from our own cluster, they look to be receding away from us. This is an observational fact. Most of the people agree. And if we start looking at the features like galaxy age, I need a universe older than 13.6 billion years, or supernova 1A data, it looks like the expansion rate is picking up pace today, meaning it is accelerating in the late time era. This is also somewhat most of the people agree upon. There are again some minority of people who try to say that you think you know about supernova, but you do not really know about supernova, therefore your conclusion based on them are erroneous. But by and large, people agree upon this. Also, people also agree that the acceleration which is caused today, which is happening today, its agent, the dark energy, has got a chance to play in the game very close to today. It did not act in the past, so it was hiding all along, and it has popped up just now. Now meaning formation of planets around that time it has started doing things. And presence of CMB, the CMB thing which we are cosmic microwave radiation, and another, its uniformity suggests that one possible explanation of its uniformity, that there was a preceding dark energy phase as well. So there is a hidden dark energy all along and it popped up. Apart from that, very early in the phase, there was another dark energy phase which is called inflation. And that inflation plus quantum mechanics applied to that gives you by and large the same average properties which we realize in our observations today. There are some shortcomings, but many of the average properties match very well with the proposal of inflation plus quantum mechanics put together. But again, there are objects like missing satellite galaxies, missing magnetic field, not enough amount of magnetic field, which casts a doubt over whether we have understood it completely or not. So this is a fact sheet. You are free to draw your own conclusions from here. But this is the standard picture what we understand. Today we are living in something called dark energy era. Before that massive object, that is called matter, that energy density was super dominant, that was driving the evolution. Before that radiation energy density was driving. Even before that, something called inflation, as we discussed, would have taken over. What happened before inflation, nobody knows. Idea of inflation is somehow tied to whatever would have happened. Inflation, whatever initial condition you throw at the beginning of inflation is a so powerful expansion, that will dilute everything away. It will make everything a vacuum kind of thing. So somewhat it hides the information what preceded inflation, but maybe some of you can come up with innovative scheme of looking at in today's observation, hint of what was lying before inflation as well. So I'm stopping here, and this is a fact sheet. You should go home and you should decide what you believe in. Okay, then we'll take questions.
Energy can neither be created nor be destroyed.
No, this is wrong statement. Energy can be created and destroyed. Yes. So again, the full statement is that class 10 physics tells us energy cannot be created and destroyed. That's it. But later on, we will see in our course as well that energy is a constant of motion as long as there is a time translation symmetry. That means nothing changes in time, then only energy is conserved. Otherwise, if energy, if there is a dynamics which is happening, conditions are changing in time, energy can change. What you want to say probably that overall, if I look for the whole collection of things where one portion is doing this thing, their energy, the whole object's energy should not change. What we call about the energy density changes in that. How dark energy was created? Just like insulation creates particles for you, similarly that you would learn from quantum mechanics. Once you have learned quantum mechanics, it will not tell you how it happens. It tells you is there a non-zero probability of it happening or not. Quantum mechanics tells you that there is a non-zero probability